Hi, welcome to our first online clip class for this lecture, and today we are going to continue to the topic of continuous probability distribution. So let's get right into it. Last time we talked about, if you remember this stuff, right? So we first have to move from the discrete to continuous part. So discrete, it means we have cases or the sample spaces where we can list all of the possible outcomes. Like if you flip two coins, head and tails, and count how many heads would that be, then you can see that there could only be 0 heads, 1 head, or 2 heads. So there are exactly 3 outcomes, and that's why we can plot that as a function there, where this on the x-axis we have all the outcomes which is x. If we define x to be the number of heads, right, then on the x-axis we have 0, 1, and 2, all the possible outcomes, all the possible values of this x, this random variable x. And for the y-axis we have the probability itself. So we have 0.25 here, 0.5 here. So this means you have a 0.5 chance, 1/2 chance to get exactly 1 head. We have 0.25 chance to get exactly 0 heads, and 0.25 chance to get exactly 2 heads. So that's what we had for the discrete part. But now we are moving to the new topic, which is the continuous part. So by continuous, it means we still have the variable x in whatever way you want to define that, but now the range of all the possible outcomes are continuous, meaning that they fall into a range of real numbers where you cannot say exactly what they are. For example, I can say that s is the height of a person. I say I grab a random person on the street and can I ask you what is your height? Not just ask, but actually measuring it using a ruler or something. I will get the number that represents his or her height, and that would be something like 178.2 or something. Okay. Maybe the next person we get for the next person like 0.638 or something. But these numbers are not actually all the possible ranges, because as we all see, if we keep measuring for the exact height, there is no exact number. I might measure that to be 175.2, but actually if I use a ruler with more precision, let me get like 0.200178 and so on. So the decimal keys that doesn't stop at any point. So that's why we cannot like have a bar for each of the possible outcomes. All the numbers can be the outcomes, and that's why when you have this kind of a random variable, we still have the graph, we still have the plot for x and y axis, but now for the x axis we just have as a range. Usually like you have to read what is being described here. If you think about height, then it makes sense if you have height from maybe 0, just make it right there, to let's say 300. Suppose we measure that in centimeters, like from 0 to 300. And once you measure like people, then you're gonna get like dots. Like for each height there is like there could be only exactly 1 person of that height. Even if another person has a height that is close to that, if you actually like measure to like a high precision, you may get 20167. So that will be different. So that means that means whoever you we measure, you get a different number every time. So then you ask that if they are all different, then what's the point of following the graph, right? Because like if you're gonna like keep adding a dot for each new height, right, you're gonna get a flat line, because they all represent just one single person whose height falls into that exact number. So that's why you have to change from this image to kind of like a curve. So the first thing we do is we change from that to curve. The second thing is, instead of having the y axis that represents the probability or the chance, we represent the chance by the area instead. So like we don't just when you plot a graph, then all these points are going to be somewhere on the y-axis. Like maybe that is like 0.3, let's say. But that being 0.3, like this point being 0.3 doesn't mean there is like 0.3 chance to get exactly that height, because there is like absolutely zero chance to get exactly that height wherever the height is, because that there's gonna be some like maybe imprecise measurement or some imperfection that make your height slightly larger or higher or smaller than that number. So it makes more sense to represent that as an area. And when we talk about area, then we can ask a more meaningful question. So now, in this case, we ask about the area. Let's say that's a 170 to 172. Right, so instead of asking for one exact number, which is impossible, we now ask for the chance where if I pick a random number on street, what's the chance that their height is between these two numbers, 170 and 172? Because now that range consists of infinitely many outcomes, 170.0505, 171.9, and so on. So now that has a meaning. Now we can interpret that as a chance of doing something, which should match our previous lecture about if you have a dartboard. Okay. Now there's no way I can hit exactly that point, but if I ask what's the chance that my dart will hit that area. Now we need to talk about area, then we can find the ratio between areas, the green area and the whole area, the area of the whole board. So now we get that, which is more meaningful. And here, this green curve is what we are going to define that as the continuous probability distribution and function. These two words are just slightly different. So let's take a look at what we define formally. So a function fx, again, is a function. You put in x, you get the value of y, the height of that graph. The function f is a continuous probability distribution function. So that's mouthful, 4 words. But we need all these 4 words for this topic to make sense. So let's start from function. What is function? Function means you put in a value x, you get a value y out. You get one single value y out. So that's a function. So what is continuous? Continuous means all the possible values of x fall into some range. Maybe like from 1 to 5, or even like from -3 to 4, depending on whether these numbers make sense in your context for your research. And what are the other two? If you remember from last time, 2 weeks ago, like for the discrete part, this word means 2 different things, which are these 2 conditions. So first we want that to be the probability, meaning that the number's hand is between 0 and 1. 0 or 1. Oh, actually I think that's a typo here. It can be higher than 1 now. Yeah, I fixed that in class. So yeah, we need that to be the probability, so that has to make sense somehow. And second thing is we want that to be the distribution, meaning that we actually cover all the cases. We don't leave any case behind. And that means all the probability or the area, in this case, or the area, has to sum up to exactly 1. Those areas have to sum up to exactly 1. I think that should be like any area between the curve is between 0 and 1. It can be more than 1 in that part. So it's continuous, it's a probability, It's a distribution and it's a function. So let's see what can we come up with some examples. Yeah, sure. So let's take a look at this function. Consider the probability distribution function f of x equals to 1 over 20 for x between 0 and 20. So now what the moment you see that range, you can say immediately that we are talking about continuous, not discrete, because there are infinitely many outcomes for x. It can be anything between these two numbers. Right? Where x, oh yeah, where x is a real number, of course. Then we are asked to find these three probability. Okay, so before we can find that, let's first start by plotting this graph. Right, f of x equals to 1 over 20. And since there is no variable on the right hand side, that means this is a constant function. It's constant. It is the same anywhere. But here is anywhere between 0 and 20. It is not yeah, then I should also specify that f of x equals to 0 for other x values. So if I want to plot a graph, I should give the values for all the points. So we have that f of x, which is 1 over 20 for in this range, and it's 0 everywhere else. So how do you plot this graph? If you are familiar with plotting graphs, you can do this pretty quick. First we want to find what are the ranges. It says 0 to 20. 0 to 20. So now we have these to the left and right endpoints. And if f of x is 1 over 20, it's a constant. It means for any point here, for any value of x here, f of x or the value of y is 120. So we get that flat line, that constant line, where you can mark that as 120. So that's the function. And also we have to specify that it's 0 everywhere else, just to make sure we don't miss anything. You notice that I also mark the 0 part on the left hand side for the negative values as well, just so that we can so that agrees with the definition. Right. So now you may ask me, what is this? Why do we have going from the left and then skip, and then we walk on the straight line and then we skip down again? Because this function is not continuous. This function is not continuous. Then where you may ask, but aren't we talking about continuous distribution function? Right? The continuous part is this range. We are talking that this range is continuous. Right? As in like the value of x, where the prob is not 0, is between that. But we are not saying anything about the function itself. The function itself doesn't have to be continuous, as in this case it's skipping even like twice. You think if I want to be like exactly correct, then I should mark that if x is 0, we get that point up there. If x is 20, if 20 is the point up there. So this is these two are blank. So anyway, that's the function. Are we happy with that? Hopefully. So now if you go back, so we have a function first. So then these two equations ask about computing the probability of the function. So start with first the probability that x is between 1 and 10. 1 and 10. What does it mean here? We have to go back to the definition and say that, to find the probability, we have to first mark 2 points. This is not to scale because one is, yeah, let me zoom in a little bit. One should be like to the left, but anyway. Right. So the prob of x to be between these two is equal to the area of this rectangle. The probability here that x falls in between 1 and 10 is the area of this rectangle. Which if you think about if you think of this pink rectangle as a dartboard, right, then it should make sense here. if you throw darts on anywhere on this dartboard, and what's the chance that the dart will lies between these lies in this range or in this interval? And if we know how to compute that area, then we know the probability. So do we know how to compute that area? The answer is yes. So this is because this is just a rectangle, we can find the area. Right, so for A we say that is the area. Right, kind of like the area. That's informal, but it's the area. And how to find the area of a rectangle? So it's the height. The height times width. The height times the width. The height here is 120. Because this is all this height from any point is 120 in this range, and the width, so it's if it's 1 to 10, then the width is difference between those two numbers, so it's 110 minus 1. So this width is 10 minus 1, and I think this is slightly too large, but yeah. So we have 1/20 times 9. So the area of this rectangle is 1/20 times 9. Which is 9/20, and that's the answer. Or if you want some decimal, you get 0.45, and that is the chance or the probability that your dart, if you throw one at random and uniformly on this board, the chance that it will land on this orange area is 0.45, which is about 0.5. And that makes sense because this area is like almost half the board, right, from start to 10, but we start from 1 instead of 0. So now we just compute the probability using the definition by computing the area. So that's the first one. The next one I'm gonna have to reuse this for because it's not sure. The next one we find the chance that x is less than 15. X is less than 15, so we can use the same graph here, and let's use blue. 15 is something like here, so we want to find the chance that x is less than 15, right? But then you might ask, wait, where is the left endpoint? I'm giving you just the right endpoint, but not left. The right is 15, where's the left one? And we have the feature that because in this case, the left, that there will be no left. Right? X can be any values any values below 15. Right? It could be 15 in this case. It could be minus 10, minus 12, minus 100, whatever values you give. But for this function, we say that the chance to get, to get to the left part is 0, because there is nothing there. There is no board on the left. Right? So even if there is like just one left or just one right endpoint, we can see that the left endpoint is the minimum here. For these questions, the left endpoint is the minimum. If there is no minimum, let's say that we get a curve that looks like that goes forever to the left, then we would actually have to compute all the areas, even if it's getting smaller and smaller. But in this case, we can see it stops at 0, and the odds or the probability is from 0 to 15. And can we compute that? Then yes. So let me say first that okay, in this for this function, the probability is the area again, right? But now it's area let's say between 0 and 15. 0 and 15. And I think my head is obstructing that. So how can we find the area? It's the height times width. The height is still 1/20 because we get a nice flat rectangle. The width now we measure from 0 to 15. 0 to 15. So that gives us 15 minus 0. 15 minus 0, and we can conclude that that's 15 divided by 20, 15/20, or 3/4, or 0.75. So for question B, the answer is 0.75, which we get immediately, directly from the area. So that's how you do problem B. And for C, we get pretty much the same problem, except we use the different direction. So now we want to find the chance, the probability that x, or that our dot is at least 12. You may notice that these two questions seems to be different. This one is asking for less than or equals to 15. This one is asking for exactly greater than 12. But recall that the probability that x equals to any single number is 0. Is it impossible to get exactly that number? So that implies that if you want to find, let's say that the prob that x is at most 15, that's gonna be equals to the probability that x is less than 15. Because we remove one point that is impossible to get. So that the probability or the area is gonna be the same. So now for C, we still repeat the same process. Even though it's greater than, we're gonna get the same number anyway. So for that, let's use purple. I'm running out of colors. So 12 is somewhere here. What if you find the chance that x is at least 12? So that's gonna give us this rectangle. Again, because for this function it stops at 20. Everywhere else is 0. It lies flat on the ground. If you get this like this curve that goes forever to the right, we would have to compute this area. But just for this one, it stops here, so that means we only compute up to this point. So the prob that x is at least 12 is again the area between 12 and the maximum value here, which is 20. 12 to 20, and we repeat the same computation. 1 over 20 times 20 minus 12, that is h over 20, if you do some math, you got 0.4, and that is the answer for C. Yes, we get like 0.45, 0.75, 0.4. So hopefully that is intuitive enough. The probability is the area between the respective part. So that's example 1. For example 2, that's gonna be similar. So you can take a look at the slide. But let me get to example 3. So in the previous 2 examples, we have a nice graph. Oh yeah, for this one, let me plot the graph for you here. Okay, so let's first start from that. So g of x is 1 over 7. 1 over 7. But for x between 0 and 11, between 4 and 11, did it say 0? Yeah, 4 and 11. So now we have 4 here somewhere, 11 here somewhere, anywhere you want to, as long as it makes sense, as long as it is positive to the right of this line. For 4 to 11, you get this. For all these values, the values of the function, for all the value of x between in this range is 1 over 7. So we get like 1 over 7 there. And again, I should specify that it is 0 anywhere else. So we're gonna get that kind of curve. Yeah, so it's like flat 0, and then we skip to 17, and then we keep at 17, and then we skip down to 0, and then that continues to be 0 forever. And we can ask the similar type of questions to find the area. Like for A, we have find the area between 5 and 8. So we can put 5 somewhere, 8 somewhere, and that probability, that number is gonna be the area. Oh, I forgot one thing. Right. We first have to check that this is indeed the distribution, probability distribution function. We kind of check that it's probability because it's at least 0. Right? But we haven't checked that it's actually a distribution. So to check that it's a distribution, we have to check that the total area is 1. We need to check that the total area is 1. And the total area here is, again, it's a rectangle, so it's height times width. Height is 17. Width is 11 minus 4. And let me erase those stuff. So that we have 1 over 7 times 7, which is 1. So we indeed get a 1. So the area of the total rectangle is 1. And once we have that, then we can start computing these values. Without that, whatever we compute won't make sense. Let me give some note that you might ask, like, can we have something like, you know, the graph right here there, and then maybe like, you know, 1/2 for 3 to 7 then? In this case, the problem is you can see hopefully immediately. The problem is this function. Let's say that's h of x. Oh, I have to remove these two endpoints. This function has a problem because the area, you know, below this curve, you know, is height times width. Height times width, which is 1/2 times 4, which is 2. That's not fun. So we said that the area is too large, it's too big. So that's not a probability distribution function. But if you actually want something that, you know, have some chance between 3 and 7, the way to fix this is you change that from 1/2 to whatever that length is for, like, so it's supposed to be 1/4. So yeah, you lower the bar from 1/2. Like if it's 1/2, it's not a probability distribution function, but if it's 1/4, then we can get a new graph now that is, you know, just that. So now the total area of this rectangle is 1, and then that's gonna make sense if you compute all the other values. If it's not 1 and we still want the same shape, the same behavior, then we just, you know, lower or make it higher to make sure that the area is now 1. So that's half of the example 2. You can look at the slide to see the complete math, but that's gonna be the same as before. So let's take a look at example 3. Do you have no? Yeah, example 3. Now we have a hopefully more interesting function. So this function is now h of x equals to x over 4 for x between 1 and 3. X between 1 and 3. Hopefully that's correct. And if you know how to plot a graph, or if you use any tools to plot this graph, we get that from 1 to 3. When x is 1, the left end point, when x is 1, h of x is 1/4. It's 1/4. So we start from here instead. 1/4. And then we can see that this one is a linear function because it has one x term times, you know, some coefficient. But anyway, it's linear. We know that the left point is 1/4, the right point is, you know, when we let x be 3, h of x or h of 3 is 3/4. So it is there. The right end point is 3/4 there. So that means when we plot the graph, we get a linear line there. So now this is the h of x, or y equals to h of x. Now that we have the probability, the graph of the probability distribution function. And of course, first we have to check if this is indeed a function, because if you see the graph this way, that means we are talking about the area under this curve. So we have to like add the lines for both ends to this image. So now we have a different shape. This shape is rhombic. I need to take too much time to think about the word. Yeah, but it's rhombic, and we have to, you know, use a formula for that thing, the rhombic. So the area here, the area of the everything. If this green curve like continues to left and right, I have to compute the area of the whole thing. But since it stops at 1, it stops at 3, so I can only compute the area between these two values. So now we have that area to be, and you have to use your favorite formula is 1/2 times width times the sum of the opposite sides. So let me write it as a plus b. I'm not sure what the formula is. So the width here is, you know, from 3 to 1, so it's 3 minus 1. This length here, this width here is 3 minus 1, which previously that is 2. And a plus b is the height and the length of this line, which is 1/4, and the height of the other line, which is b, is 3/4. And if we compute the whole thing, and if we compute everything, we're gonna get like 1/2 times 2 times 1, which is 1. So this thing area makes sense. Now it's a probability distribution function. And if that is a PDF, the probability distribution function, then we can compute all these 3 values. Alright, so let's compute them. So what's the first one? The prob that x is between 1 and 2. So now this we have to it's 1 and 2, so the left point is 1, which is there. The right point is 2. So the first question is asking us to compute the area of this rhombic again. It's not rhombic, right? It's something else here. Trapezoid. Oh, it took me forever to. Yes, yeah, of this trapezoid. So for the question A, we say that okay, the probability of that thing is the area of the trapezoid. And again, we use the same formula as 1/2 times the width. It's from 1 to 2. So this width, that is this width is 2 minus 1. The height of the left hand side, this length is still 1/4. But the right hand side is we have to figure out. So if x is 2, we have to find the value of y. We're going to find this point. Right, to compute this length, we have to know this point. If x is 2, then what is y? If x is 2, then y is h of 2. And h of 2 is in this for this formula is 1/2. If this is 2, this is 1/2. So we can say that's 1/2 here. So now it's 1/4 plus 1/2. So the area of this blue trapezoid is 1/2 times the width, which is 1 plus the sum of the parallel sides, 1/2 plus 1/4 plus 1/2, which should be 3/4. And that product happens to be 3/8. So we say that the chance, the probability that our dots will land between 1 and 2 is 3/8, which is kind of close to 1/2. You know, it's close to 4/8. So that's reasonable. So that's the first question. The second question, question B. So we are asked about the area to the left of the point 3. So where's 3? 3 is there. Oh, where's 3? 3 is there. Right? So we start from that, and then we kind of pinch all the way to the left. And for this function, it stops here. So this thing is the area of the trapezoid of this pink trapezoid. Don't worry about the word, but you can see that this actually looks like this is actually the whole thing. Like it was the same area as we just computed previously, but since it's the whole thing, and we know that the whole thing, the area of the whole shape, and the area under the curve of the whole shape is 1, so we can say without having to compute again that is 1. In other words, we will always hit the board that is to the left of 3. Wherever our dot is, it's gonna be less than 3, less than or equals to 3. In this case, so now we get 1. We would have to compute the area if we didn't know it's the whole thing, but now we know, so we can skip that and say it's 1. And lastly, we compute the C, the prob that x is greater than 2. So let me reuse the same image here. 2 is there. If x is greater than 2, so we are looking for the area to the right of that point. So that's where we're gonna compute next. So see, the prob that x is greater than 2 is again the area of the trapezoid, which is 1/2 times the width. We can find this width. This is 3 minus 2. and the sum of the heights. This height we just compute. We didn't have to do it again. We just computed this 1/2. And the right side is 3/4 because we just compute previously that its point is 3/4, and we just do the math. That should give you 5/4. 1/2 times 1 times 5/4, that's 5/8, and that's the answer. The probability that x is at least 2, x is greater than 2, is 5/8. Which makes sense in two ways. First, it is less than 1, less than or equals to 1. Second, if you actually compare the A and C, if you compare the A, the pink one, and C, the orange one, you can see that these two areas, if we add these two areas up, you will get the whole thing. If you add these two areas, we get the whole pink part, and you can see that the numbers add up to 1. Maybe because 3x plus 5x is 1. So it makes sense that wherever all that hits is either between 1 and 2, or it is at least 2. It has to be either in the blue part or the orange part. There is nothing else in this flow. So that's the example 3. And now we're gonna move on to the next part for the properties of this function. Stay tuned.